In the last lecture, we talked about an empirical method for finding shape factors. This is used in the industry when you have complex shapes and you may not be easily able to find a standard expression for that. So, here is an example where you have the object dA1 here and you want to find dA1 to dA2. Okay. And so, you put a sphere on top, a translucent sphere, and the image of dA2 will fall on this unit sphere, and you take a camera out here and take a picture of this area A2, and you will get this area AB as a picture. Now, we want to show that f dA1 dA2 is nothing but area of that image by pi. So, first we look at the expression f dA1 dA2, which is 1 over pi integral over A2 is area of cos theta 1 cos theta 2 dA2 by s square, okay, where theta 1 is angle between the line joining these two areas and the normal of dA1. Now, when you come on the sphere, the big advantage, as you know, is that the line joining the center of this hemisphere to the object here DAS is normal to that line. So, theta 2 here is 90 degrees. So, that will go away. Your cos theta 1 d omega 1 and d omega is the angle subtended by DAS and dA1, and on a sphere when you integrate this one, you will get it as ds by r square, this area by r square, r is a constant. So, when you integrate this, you will get as cos theta 1, as cos theta 1 is nothing but AB. So, finally, you will get d1 d2 AB by pi r square. If you take r as unity, nothing but AB by pi. So, this is a simple way to calculate shape factors empirically, and is useful in practical situations where the objects of complex shape and you may not be in a position to do either the double integration or obtain the shape factor from any simple tables available in books. So, with this we have covered all aspects of both estimating the radiative property surfaces, that is emissivity, absorptivity, reflectivity. We also covered how to calculate the fraction of radiation leaving one surface which arrives at another surface. So, now we have got all the tools necessary to solve real problems. So, the real problems we are dealing is in radiative heat transfer between surfaces. So, we will not look at radiative transfer in enclosures. What is the enclosure? Enclosure is nothing but a series of surfaces which enclose a given area. Not all surfaces in enclosure need to be actual surfaces, some of them can be imaginary surfaces for convenience. So, here is enclosure consisting of 1, 2, 3, 4, 5 surfaces and an opening which I can close by a dotted line, that is a virtual surface. So, you have a 1, 2, 3, 4, 5, 6 surface enclosure. The concept of enclosure is useful because ultimately the radiation leaving any one surface has to reach some surface in the enclosure. So, it is a closed system and it makes analysis of radiation transfer very easy. Now, the first example we will take up is enclosure consisting of only black surface, there is no reflections involved. This is the simplest case and this makes analysis extremely easy. So, first we look at this case and develop our methodology, then we go on to more complex. Let there be n surface in the enclosure, capital N, and for each surface that, let us say this is the, let us say the ith surface, the heat added to the surface is Q I, and assume all surfaces are isothermal uniform. This is not a very restrictive assumption, because in case this surface is not isothermal, we can divide it into 10 subsurfaces, each of them can be assumed to be isothermal. So, you can divide any real surface in which there is a temperature gradient into large number of small surfaces, each one of them can be assumed to be isothermal. So, this is a problem easy to do, and today with the availability of computer, n can be as large as you want, can be 1000, 5000, there is no problem, you can easily solve these equations. So, for the ith surface enclosure, the energy to be added is energy emitted minus energy absorbed. So, this is first law. Right. So, all you have to do, and this is all black surfaces. So, life is very easy. So, energy emitted by the ith surface is nothing but sigma Ti to the power of 4 into Ai. That is the total radiation emitted by that surface in watts. This is also in watts. And the radiation absorbed, we look at the jth surface, which emits this much radiation, and ask what fraction of this radiation reaches surface I, that will be F G I. We used to call it F A J A I, but that is a bit difficult to write. So, I am writing F J I, which is a fraction of the radiation emitted by the jth surface which reaches the ith surface, and you sum over all j surfaces in the enclosure, all the n surface enclosure. So, here is the expression which relates the heat to be added to the enclosure. If the amount of radiation emitted by the surface A I is larger than the amount which is absorbed, you have to add heat to the surface to keep it isothermal and steady state, and that heat is Q I. So, if the energy emitted is more than energy absorbed, you have to add heat to it, that is Q I is positive. On the other hand, if the energy emitted is less than energy absorbed and you remove heat, then Q I is negative. So, so that is the result we have. Now, we also now we are going to simplify this equation. We know that sigma F I to j, j equals 1 to n is equal to 1, we know that. Sum of all the shape factors in an enclosure is equal to 1. So, I can multiply this by 1. So, I will do that in the next version of this expression. So, I am going to write this as sigma j 1 to n, sigma Ti to the power of 4 Ai F I j minus what is absorbed sigma T is by A j F j to I. Okay. So, this I merely have added this, and sigma j to 1 F I j is 1, I have just added multiplied with this. Now, I am going to use reciprocity, and reciprocity says that A j F j I is A I F I j. So, I can take A I F I j common, okay, and write this as sigma T I to the power of 4 minus T to the power of 4 into A I F I j. So, I have used reciprocity here. So that this becomes AI Fij. Okay. So now we have a very simple expression, and this can be present further in a more elegant form, which enables us to interpret it physically why I have written it this way? We want to now interpret this result which we have obtained regarding radiative transfer between different surfaces as the potential difference between the node I and the node J divided by a resistance. So, this you look upon as a thermal resistance to radiation, and this term really is the potential difference. So, we have a nice electrical analogy for radiation, wherein this current, this can be looked on as a current, let us call it the heat current. Heat current is equal to difference in potential between the two nodes I and J divided by the resistance between the two surfaces. So, let us now illustrate this with a very simple example. Suppose we have two parallel black plates. Okay. Let us say they are infinitely long, so it makes it easy. Surface 1, surface 2. So, by electric analogy, we will say surface 1 has a potential sigma T1 to the power of 4, and the resistance between two surfaces is given by this, and the surface 2 is sigma T2 to the power of 4, and therefore, Q 1 to 2 nothing but the difference in potential divided by the resistance. So, this is a very simple way to understand the result for this case. So, you have two surfaces and the flow of heat or current in the analogy is due to the potential difference, which is sigma T to the power of 4 in this case, divided by the resistance. Now, notice that this resistance occurs primarily due to the geometry of the problem. So, this we will call it as geometric resistance. Because this resistance arises on account of the relative configuration of the two surfaces, which is a consequence of the geometry of the problem. And this is an interesting example, but it is only two surfaces. Suppose we had three surface enclosure. One, 2 and 3. How would this thing change? It will get a little complicated, as you can imagine. So, 3 surface enclosure, I have to draw 3 potential, 3 batteries. Now, so we will have one resistance between these two, another resistance in these two, and another resistance in these two. this will be 1 over A1 F13, this will be 1 over A2 F23, this will be 1 over A2 F21. So, this is a triangle. So, if you are well versed in electrical circuit theory, you should be able to solve this delta network using standard theorems in electrical engineering. But you must remember that this is only this kind of electrical analogy we are giving only for the convenience of your understanding the problem. Today, in reality, as soon as you go to more than 2 surfaces, 3, 4 or 5 surfaces, you are going to use a computer. You will write down the expression for the various surfaces and you will get 3 equations for the 3 unknowns T1, T2 and T3, and you will invert this matrix very quickly using computer. So, final method of solution is matrix algebra, but in order to have a physical understanding of the various factors controlling the heat transfer between surfaces, it is good to draw electrical net. For example, suppose this is very small, is very tending to 0. So, this circuit will open up, then the current flow from 1 to 3 is only through 2, and let us say 2 was adiabatic surface, then the current has to only go this way, no current can flow through this arm. So, that makes your interpretation and analysis of the results very easy. So, we are going to use electrical analogy mainly as aid to understanding what is happening in a given radiative transfer problem. The actual numerical solution is best done through solving a set of simultaneous equation using standard tools available today on the computer. So, this was for an enclosure consisting of black surfaces. Now, we move on to something more ambitious and look for radiative transfer between non-black. Before that, let me just do one example, so that you are, imagine a duct. And let us say you are trying to measure the gas flowing in a duct using a thermocouple. And let us assume that the walls of the duct are 600 K and the duct is black. Okay. And the thermocouple is also assumed to be black, both are, duct is black and thermocouple also assumed to be black for convenience. And you want to know what is the error in the measurement temperature by thermocouple, because the thermocouple is supposed to measure the temperature of the gas flowing in the stream. But the temperature recorded by thermocouple Tc will not be equal to Tg. Why is that? That is because the heat transfer from the gas to thermocouple will be by convection, and that can be written as H into area of the thermocouple into Tg minus T thermocouple, and this has to balance the heat loss by the thermocouple to the duct. So, on account of this balance, Tg will not be equal to Tc, and our interest is to understand what is the error in temperature measurement. our aim is to measure the temperature of the gas, but the thermocouple will not get the temperature of the gas, because the temperature of thermocouple will be in between the temperature of the gas and temperature of the duct. Okay. So, if you take a typical example, suppose the thermocouple is reading 800 K and the duct we have assumed is a 600 K, and let us assume that the heat transfer coefficient in this case for convenience is around 50 watts a meter square degree Kelvin, typical for gas flow at reasonably high velocities. If you put all this in, you will get the temperature of the gas as 10,080 Kelvin. So, the error of measurement of gas temperature is quite large. It is the difference between the thermocouple temperature and gas temperature, which is 280 degree Kelvin, divided by the gas temperature. So, this error is pretty large. Okay. So, an error of 280 Kelvin is unacceptable. Hence, what one can do to reduce this error? One way to do it is shield the thermocouple. So, thermocouple has a shield which ensures that the thermocouple does not directly see the wall of the cold wall of the duct, and so thereby reduce this error of 280 Kelvin to a much more reasonable number. Now, this we will see in the subsequent example, how a radiation shield can reduce error in measurement of temperature. As a matter of fact, in meteorology, where routinely temperatures are measured outdoors, one of the sources of error is the fact that sunlight might directly fall on the thermocouple or on the thermometer. So, you tend to either shield the thermometer or provide a special enclosure, which is a shield really, inside which the thermometer is kept. So, all these are attempts to ensure that the thermocouple or thermometer actually measures the gas temperature or air temperature, and not the temperature due to the heating by the sun or due to the fact that this thermocouple may lose heat to a cold sink somewhere. Now, we will take it up very soon, the role of shield, but before we do that, we have to do some more realistic examples. So, we will look at enclosure with gray diffuse isotropic surfaces. So, the problem now is a little more realistic, not just an enclosure with black surfaces, which is rather rare. Now, we have a surface, all the surface enclosure are diffuse isotropic surface. That means, they reflect and emit in a diffuse isotropic fashion. So, that the angular effects are very simple. But we will make this approximation of gray surface, which we had earlier argued is not very common, but this is a starting point for our analysis. So, we will start with the gray surface, but later on we will also look at non-gray. Now, in gray surface, remember suppose your surface I, not only is the surface I emitting radiation equal to this much, it is also reflecting radiation. Okay. So, the reflected radiation is reflectivity of the surface to Hi, which is the incoming radiation. So, the total energy leaving the surface is a sum of emission and reflection. Okay. Radiation leaving surface is equal to emission plus reflection. So, as you count the photons coming out of a surface, either they are photons emitted by the surface or they are photons which are reflected of the radiation that is incident on the surface. Okay. So, this is epsilon I sigma Ti to the power of 4 plus rho I Hi. Now, this quantity will come frequently in gray enclosures, because in contrast to black enclosures where you only have emission, no reflection. In a gray enclosure you must worry about both emission and reflection. Since this is going to come very often, we will give it a new name called radiosity. So, radiosity is nothing but radiation leaving a surface, that is sum of emission per reflection, per unit area. So, radiation leaving a surface per unit area in watts per meter squared consists of two components, the emission and the reflection. And since you are dealing with gray diffuse isotropic surfaces, you can write this also as 1 minus epsilon I Hi using Kirchhoff's law. Now, this is the basic building block, the idea of radiosity, and the advantage of radiosity is as follows. First thing, on the ith surface, the heat to be added is nothing but energy leaving the ith surface, energy incident on the ith surface multiplied by Ai. So, this is radiosity, what is leaving, this is irradiation, what is arriving. So, if you take a surface I and put a little control volume there, you can see that radiation Hi is coming and radiosity Bi is leaving. So, difference between Bi Hi is a measure of how much heat you must add to maintain this surface at a constant temperature Ti. Okay. So, this is a simple equation. You also recognize this problem can be written another way. Heat to be added is also equal to, like we did for black, energy emitted minus energy absorbed. Both is equivalent. One is treatment using control volume. You actually do not worry about the process of absorption, deflection and emission. You merely count the photons coming in and photons going out, and the difference between them has to be balanced by the heat added. On the other hand, if you look at the surface and ask how much energy is absorbed, this energy coming into the surface, absorbed is alpha I, so that much is absorbed, and this is energy emitted. Using Kirchhoff's law, you can write this also as that is also an equivalent statement of the same expression. One is through the concept of radiosity and the other is through the concept of absorption minus emission. Both are equivalent, and we will be using this interchangeably to get information about any given problem. Now, the next question you would like to ask is, what is Hi? Amount of energy arriving at the surface I is Hi. This has to be equal to energy leaving surface J, Bj Aj, times the fraction of radiation leaving J and arriving at I. So, the logic is same as what we did by black enclosure, except that instead of sigma T to the power of 4, the black body emission, we are using the concept of radiosity. So, radiosity is a convenient way to handle problems where there is both emission and reflection. So, it combines both. This is total energy leaving surface J into area of J, and this is a fraction arriving surface I. Now, you have to sum over all surfaces J 1 to n. That is your incoming radiation surface I. Now, let us combine all that and see how it looks like. So, in surface I, radiation leaving surface I is Bi Ai minus Hi Ai, that I am going to now write as sigma J equals 1 to n, energy leaving surface J Aj F J to I. Okay. Like we did earlier for the case of black surfaces, you can multiply up and down by multiply by 1 here, which is sigma Fi A I J J equal to 1 to n. This is equal to 1, we know that. Equal to, actually, I am sorry. Sigma F I J J equal to 1. I multiply that by 1 here. So, I have sigma J 1 to n B I A I F I J minus B J A J F J I. Okay. And again I use reciprocity, A I F I J is A J F J I. So, I get a very clean result once more. So, this you must recognize is exactly same as the expression we obtained earlier for enclosure with black surfaces, but now instead of sigma T to the power of 4, our potential difference is the radiosity. Okay. So, that is the only difference that that is appearing there. So, once you recognize that, it will be quite easy to proceed further. We can also combine the two expressions we derived for the heat transfer, and we can write the Qi by eliminating the irradiation, can write as sigma Ti to the power of 4 minus Bi into epsilon I by 1 minus epsilon I into Ai. Now, this comes in by combining the two equations we wrote for Qi in the a few minutes back and eliminating Hi from the equation, the radiation, get the expression, and this can be written in a very useful way as 1 minus epsilon I by epsilon I Ai. Why is this so useful? This is so useful because what it says is, if you take a surface with a certain potential, it shows there is a resistance between that and the radiosity point Bi, and that is due to the surface not being a black surface, and hence this quantity is called the surface resistance. So, this must be contrasted with the concept of geometric resistance, which we derived a few minutes ago, which was 1 over A I Fij. So, this is purely a geometric factor, this resistance. This resistance is fundamentally dependent on surface properties. When emissivity of surface I is 1, this term drops out completely, does not exist. It exists only when the surface is not a black body, then there is a resistance. So, if the surface black body, these two are equal, the radiosity point is same as black body emission points or not. Now, let us write expression now for 3 sub enclosure, so that we understand what we have achieved here. The 3 sub enclosure now, we will write surface 1, then we will have 1 resistance, surface 2, it has own resistance, surface 3, it has its own resistance. So, this is 1 minus epsilon 1 A 1, this is 1 minus epsilon 2 A 2, this is 1 minus epsilon 3 A 3, and the 3 radiosity points B 2, B 1 and B 3 can now be joined by surface resistance notation. Which we saw earlier. So, this will be, sorry, it will be 1 here, be 1 point. So, this is 1 over A 1 F 1 3, this is 1 over A 2 F 2 3, this is 1 over A 1 F 1 2. So, we have the complete resistance diagram now for an enclosure consisting of 3 gray diffuse isotropic surfaces, and they consist of 3 potentials here, and then we have 3 surface resistance terms, because the surface is not a black body, and 3 geometric resistance terms on account of the relative configuration of the 3 surfaces. So, this circuit we have drawn, but you can see this is quite complicated, may not be easy to solve as it is, but for certain simple cases this can yield very nice results. Let us take a very simple case first. Let us take a 2 infinite parallel plates with emissivity epsilon 1 epsilon 2. Assume there is no other surface. So, F 1 2 is 1, because infinite parallel plates. So, one can write the electrical analogy for this case as 1 minus epsilon 1 A 1, this is sigma T 1 to the power of 4. Then between the 2 surfaces, this is 1 over A 1 F 1 2, but F 1 2 is 1. So, you can write it, and this is equal to 1. Then we have the other surface, its surface resistance, and then you have the second pattern. Therefore, Q, and let us now say both plates are equal area and large, then you have Q from 1 to 2 is sigma T1 to the power of 4 minus T2 to the power of 4 divided by, this area is common, you can take the area out up there. So, we will get 1 by epsilon 1 plus 1 by epsilon 2 minus 1. A very simple result. This is minus 1, minus 2, plus 1, that is what you are getting. And so, this is the expression for radiative heat transfer between two infinite parallel plates, and it clearly shows that the major geometric resistance is right here, coming from here. And you can see that if you want to reduce heat transfer between two parallel plates, then you have to let epsilon 1 and epsilon 2 become very, very small. They become very, very small, the denominator here becomes very large, and it reduces the heat transfer between the two surfaces. This is used in practice in insulation application. So, if you want to insulate a particular object, you take large number of reflective surfaces and you line them up. So, you have large number of reflective layers. These are nothing but plastic, thin plastic sheets coated with aluminum, and so the emissivity tends to be typically of the order of 0.1 or less. So, if you just take two parallel plates, you can see that Q1 to 2 is sigma so let us say this is epsilon 1 is equal to epsilon 2 equal to 0.1. So, this will be 10 plus 10 20. So, what will happen is you will reduce heat transfer by a factor almost 1/20th of what you would have if there was no, it was only black surfaces. If it was only black surfaces, you will get the expression in the numerator. By having reflective gray diffuse surfaces with emissivities of the order of 0.1, you are able to reduce the heat transfer by a factor of 19 times. So, this is now a very common application both in spacecraft as well as in other applications on the ground, where you cover a surface to be insulated with a large thin parallel sheets of plastic coated with metal like aluminum, and this is very inexpensive and very effective insulator you can have. Of course, you must remember that this works extremely well in space where there is no other mode of heat transfer except radiation, but on the ground there will always also be convection between the plates. So, you have cut down radiation, but you cannot cut down convection. So, the convection will pose some problem for you, but you can reduce convection by evacuation, by reducing the amount of matter between the two surfaces, reduce the pressure that the number of molecules between the two surfaces small, then you cut down the convective heat transfer between the two plates. In space, of course, there is vacuum. So, there is no other mode other than radiation. So, it works very, very well, but on the ground also you can use it effectively, provided you can find some other ways to suppress convection. Now, let us take an example now to illustrate this issue further. So, suppose you put between two plates a shield. Okay. And before I take the shield example, let us now take a simple example, steam pipe. Let us say the outside steam pipe is at 400 Kelvin, about 127 degrees centigrade, and its emissivity is 0.8. Okay. And you would like to know what is the heat loss by radiation to the room. It is surrounded and put in a room, and the room walls are at 300 K. Okay, now this problem can be solved very simply. Treat the pipe as a surface and surrounded by this one, and you can do a simple resistance model. Let us take this surface as 1 and this surface as 2. So, we have sigma T1 to the power of 4, 1 by epsilon 1 A1, 1 by A1 F12, which is 1 by A1 because F12 is 1, and of course, you have the room. Let us assume room to be a black body. Room emissivity is 1. So, we will get now sigma T2 to the power of 4. Therefore, heat transfer rate per unit area of the pipe is nothing but epsilon 1 times sigma, of course, T1 to the power of 4 minus T2 to the power of 4. Okay. So, what actually happens is that the minus and plus cancel out, only 1 over epsilon left behind, which comes here. So, this now I can estimate because emissivity is 0.8, T1 is 400 K, T2 is 300 K, and you will get a number like 794 watts per meter square. Okay. So, that is the kind of heat loss that you are talking about. Now, notice that this heat loss is very large. So, this heat loss is more than the heat loss by free convection from the steam. So, it really is useful now to add some insulation on the steam tube, reduce the heat loss not only by conduction, but also by radiation. Okay. So, this is one example of typical application in the industry where a pipe containing steam going long distances will cause large heat losses, which are inevitable. Now, let us go to the example of the thermocouple shield. So, we thought of a wall of a duct with a thermocouple there, and you put a shield here. Okay. Let us say emissivity of the thermocouple is now 0.5. The shield thermocouple is a emissivity of 0.4, just for convenience. Let us say thermocouple measures the temperature of 800 K, and we would like to know what is the actual gas temperature with the shield there. So, your shield is now surface 2, the duct wall is surface 3, and thermocouple is surface 1. Okay. So, you can calculate the heat transfer from the shield to the thermocouple to the shield, and heat transfer can be written as sigma T1 to the power of 4 minus T2 to the power of 4, divided by 1 over epsilon 1 A1 by A2 1 over epsilon 2 minus 1. This comes by writing down the electrical analogy between electrical circuit 1 and 2. This is heat transfer rate plus, so this is equal to this radiant transfer from the thermocouple to the shield has to be equal to that from the gas to the shield to thermocouple. So, this is a balance between rate transfer from thermocouple to shield with convective transfer from gas to shield. Okay. We know the thermocouple temperature, which is taken as 800 K. We want to know the gas temperature given the measured temperature, and we do not know the shield temperature. So, there are two unknowns, Tg and T2. So, you write down one more energy balance. This is for the shield. For the shield, first thing is radiate transfer between the shield and the duct. That is straightforward, same as what you have done before. Then what you just now derived between the shield and the thermocouple. And this has to be equal to heat lost by shield by convection, or gain, I am sorry, by convection. So, this is radiative loss to duct, this is radiative, this will be radiative gain, this will be the radiative loss to, I am sorry, thermocouple. This is the radiative gain from, sorry, this convective gain from gas. So, now we have two unknowns, you can solve for it, it has to be done numerically. So, we solve for it, you will find that if T of the thermocouple is 800, heat transfer coefficient, gas heat transfer coefficient is 113.4 watts per meter square Kelvin. This is typical value for high speed flow in a duct. Then, and we already assumed epsilon thermocouple is 0.5, epsilon of the shield is 0.4. You will find that the temperature of the gas will come out around 808 Kelvin. While that of the shield will be 779. Now, this clearly illustrates the important role. When the shield was not there, we had an error of the order of 208 degrees Kelvin. When you put the shield, the thermocouple was not directly seeing the wall of the duct, and it was exchanging radiation only with the shield. The shield already had a high temperature. So, radiative loss of the thermocouple to shield became small. So, the temperature of the shield went closer to the gas temperature. So, now you can see there is only around and 1% error. So, 8 Kelvin error, which is equivalent to 1%. So, we reduce the error from almost 25% to 1% by just adding one shield. So, using of shield is a very popular measure in the measurement of temperature, because it drastically reduces the error introduced due to radiative heat transfer. So, this example we took showed clearly the importance of shield in reducing the error, and this was done by using simple shape factors and radiative transfer enclosures. So, we will continue along this line and look for more complicated examples in the next lecture, and we will see how to extend this idea to a much more complex problem as well as more realistic problems, including those which are non-gray. Thank you.